Welcome to our new session. In this session, our target is to talk about the datum and map module in Leica Infinity. But before going to it, we need to understand some theory behind. So we are going to talk about the coordinate system and HeightModes first. So let's talk first about the joint. What is the joint? It is equipotential surface that best equates to the mean sea level. Actually, it is an imaginary surface which does not exist. It is imaginary surface, so actually we need some instrument to detect. We also have the ellipsoid. Ellipsoid is an ellipse which is mathematically defined, and to know the parameters of this one, if you know the parameters, which is A and B or A and F, we know everything about this ellipsoid. Actually, there is many ellipsoids available, and each country is selecting the best one which fits to it. For example, if you can see this one, the red one is fitting quite well with the North America. This one is fitting quite well with that area, and so. So actually each country is selecting the local datum which fits with it. Also, we have the WGS84 ellipsoid, and all GNSS systems are using WGS84 ellipsoid. So actually, if you are working with a GNSS, you are obtaining coordinates in WGS84. As we mentioned, we have some local ellipsoid, and each country selecting the suitable one, which fits with the geometry of the country. Now we are going to talk about the Cartesian and geodetic coordinates. You can see this is the shape of the Cartesian coordinates. It is X, Y, and Z. And you can see this, the Z value is very large or very big value, as it is measured from the center of the ellipsoid. On the other side, we have the geodetic coordinates, which is latitude, longitude, and ellipsoidal height. So actually, it is this one. It comes as degree, minute, and seconds. And N indicates we are in the northern hemisphere, and east indicates we are working in the east side of the Greenwich Mean Line. To convert from Cartesian to geodetic, or from geodetic to Cartesian, we need to know the ellipsoid. In this case, we are working with WGS84, so we need to know the parameters of WGS84 ellipsoid. Actually, if we are talking about any point B, actually you can find that the same point, maybe it has several coordinates. So the coordinates of P may be measured from the WGS84 ellipsoid, or it can be measured from the local ellipsoid or local datum. So actually, to know the coordinates of this point in the local datum, we need to make something called transformation, which will link the two reference frames. So actually, if we have a point P and I need to know its coordinates in the local Cartesian, so I'm going to the local site and I need to go make it in Cartesian, I need a classical 3D transformation. I need to know this classical 3D transformation, which we are talking about 7 parameters, which they are 3 translation, 3 rotation, and 1 scale factor. Okay, now we are in the local site and we have the Cartesian coordinates. Can we get the geodetic coordinates? Yes. Like the case in WGS84-1, just we need to know the parameters of the local ellipsoid. So this is A and B of the local coordinates of the local ellipsoid. So in this case, I get this one. So, but actually all the surveyors are working with something called N and E, north and east and height. So actually we need to make something called projection to obtain these coordinates. Actually we have many projection types, and each country selecting one of these projection or one and more and from this projection and are used in this country. So if we want to make a projection, we need to have the latitude and longitude coordinates. After that, we can make this projection and obtain E and N and height. So in this case, we need to define our projection. This graph summarizes what we were talking about. So in the beginning, we have WGS84 coordinates obtained by the GNSS system in geodetic coordinates. We can convert to Cartesian, just we need the WGS84 ellipsoid. If I want to go to the local side, so actually I need to move from the Cartesian to the other Cartesian, I need to have the classical 3D transformation, so I need 7 parameters. So it is now I moved from the classical 3D transform using the classical 3D transformation to the Cartesian in the local side. I need to know the local ellipsoid parameters so I can get the geodetic coordinates, and when I get the geodetic coordinates, I need to apply the projection to get the grid coordinates. So actually it should be like this. From geodetic, I can go in the WGS84 side. From geodetic, I need to go to the Cartesian side using the WGS84 parameters, ellipsoid parameters. After that, I need to move from the Cartesian to the other Cartesian, and I need in that case to know the classical 3D or one step, which we'll talk about it later. After that, from the Cartesian, I need to go to geodetic in the local side. I need to know the local ellipsoid, and after that I can make the projection to get the grid coordinates. Actually, to make this transformation from one datum, from WGS84 for example, to this one, the local side, we need to have some points, common points, which is covering the area. So in this case, we can see this is when it's a good distribution, these 4 points are covering the whole area. This one is not a good distribution, and some points are outside the coverage area. So points outside this area will not be good. The transformation, we cannot guarantee the transformation of these points. So the classical 3D transformation, you can see this is, we need 3 translations, delta x, delta y, delta z, and 3 rotations and 1 scale factor. To make this one, we can calculate for sure using Leica Infinity or Leica LGO. We need at least 3 common points in position and height. We must know local ellipsoid, and we must know the map projection and geoid if required. So actually, this is one constraint. We need to know the local ellipsoid, and we need to know the projection we are using. Its advantage, it can be used over any size or area. So what is the limitation of the classical 3D? As we mentioned, we must know local ellipsoid and projection. Actually, it cannot be used for arbitrary grid. For example, I cannot get coordinates like 1000 and 1000, and I need to use a classical 3D transformation. It is not possible to use. Needs at least 3 common points known in position and height. Actually, position and height cannot be treated separately. So each point must have position and height. This is just a summary for what we said. It is creating 7 parameters, 3 shifts, 3 rotation, 1 scale factor. It converts from WGS84 to local. It is maintaining the accuracy of the GPS. The distortion of the map projection are taken into account, which enables you to use the kind of transformation for larger area. The disadvantage, the local ellipsoid and map projection must be known. The usage if you wish to keep GPS measurement totally homogeneous and information about the local map projection is available, the classical 3D approach would be the most suitable. At least 3 points must be available in both systems. Okay, so what is next? If you don't have the information about the local ellipsoid or projection and both, we can go for the one step. How it works? Actually, WJCT4 coordinates are projected on a preliminary grid using a temporary transverse Mercator projection. TM is one of the projection type. This gives grid coordinates from WJCT4 coordinates. After that, we are making something like a classical 2D transformation, and actually height is treated separately. Actually, this step is done in the background. We don't feel it using the Infinity or LGO. So how it works in the WJCT4 side, actually you are making temporary TM projection to get these grid coordinates, and actually I'm making classical 2D transformation. So the one-step transformation is making this one, getting from the geodetic side or Cartesian side to the grid side, and now I have the coordinates. The main advantage here is the height and the position transformation are treated separately. So if you have some points which have good position but bad height, I can use this one. If I have some position which has good height but bad position, I can use this one separately. As we mentioned, the position transformation WJCT coordinates are projected into a temporary transverse Mercator, and the height transformation is a single dimensional height approximation. The main advantage: no knowledge is needed for local ellipsoid and map projection. Parameters may be computed within the minimum number of points. Errors in height don't propagate into the error in position. The disadvantage of this one, the area of the transformation is restricted to about 10 square kilometers. The usage for cases where there is no information regarding the ellipsoid and or map projection, and or you wish to force GPS measurement to tie with local existing control, for example coming from TPS. Now we want to talk about the height models. What is the orthometric height and what is the ellipsoidal height? As we mentioned, GPS or GNSS systems are working on the ellipsoid, so they are offering us the ellipsoidal height, which is a small h. But actually we need to know the orthometric height, which is measured from the joints. So you can see here we have something called capital H, which is measured from the joint itself. So this is the ellipsoid and this is small h, and we have the joint and we have capital H, and we have something called joint ellipsoid separation or undulation, N, capital N. So actually if we know any two of them, we can get the third one. So the equation is small h equals capital H plus N, where h is the ellipsoidal height, small, the capital H is the orthometric height, and N is the joint separation.